I'm going to introduce you to our moderator for today, Mr. Elias Rigas. He serves as a U.S. Army Research Laboratory Vehicle Technology Directorate Chief of the Vehicle Applied Research Division. He's responsible for helping to develop the tactical and strategic vision for the Vehicle Applied Research Division at ARL. He will be introducing you to all of the panelists for today, so please join me in welcoming Elias up here.
Well, thank you all very much. It's really an honor and a pleasure to be up here and to be working with these a lot of great folks and really industry giants here. It made me feel really young when I kept hearing all these folks from '78 and earlier. As a class of 1991 graduate, I thought I was old, but it just shows me that there's a lot more time ahead for all of us. A lot more time to make an impact, a lot more time to do great things, and so I'm really excited to be here with the industry folks that have been here for such a long time and researchers, as well as all the young folks that are up and coming now that are really going to be driving this industry. And I think we have really an exciting area here in eVTOL that's emerging. We've done a lot of work both ourselves in the Army Research Laboratory and the Army community in large-scale systems, as well as small handheld, but I think there's a confluence now where we have these small electrical, cyber-physical, biosystems that are really coming together in this range where we can really take a strong look at these electric VTOL systems, which I think are going to be a paradigm changer both for industry and for the military. And so we're really excited about what's happening in this space. We're really starting to set ourselves up and establish ourselves up both in the Army and in other places, start to take a look at these capabilities, look at these technologies, and how we can really push them forward to really advance the capabilities that, from our perspective, the soldier needs, but from the MOVE perspective, partnering with folks like Farhan and the MOVE Center, really being able to help, support efforts and support projects and programs that will really help be beneficial to both ends, both the commercial side and on the military side. And so you'll hear a number of speakers here today talk a little bit both from strategic priorities and frameworks, large-scale systems, and from our industry partners talking about the challenges that they're facing at a large scale, as well as kind of the things that they're kind of starting to look at from a research perspective and a longer-term perspective. And then we'll finish up with some of the really fundamental research work that's going on both in the university side and the government side in terms of the technologies that we're thinking about longer term to really solve some of the big challenging problems in this eVTOL space. And so you didn't come here to listen to me, so without further ado, I just wanted to introduce Mr. Scott Drennan. Scott's been with Bell Innovations for about 25 years now. He received his BS from the University of Maryland. He's right down the road from us, and as well as a master's degree from Southern Methodist University. He's been focused really on VTOL technologies and configurations, working on a lot of really important programs for the military, like the V-22, and more recently things like the Bell 609 program. He's part of NASA's Advisory Council for Aeronautics, and he's proud to really work for Bell. And we're really glad to have Scott as a partner, both for the Center for MOVE and for the rest of us here. We've worked with Scott, and we've been working with him as well, too, from the Army side. Very amenable to partnering. Like Dr. Lewis mentioned, we're very interested now in partnering from our perspective. And ARL, from where I come from, is really developing a new ecosystem of how we operate, working alongside industry and government and really trying to drive innovation to the users and to the folks who will actually build those types of systems like Dr. Lewis mentioned. And so we don't want to hold technology. We want to get technology out to the folks that can really put it onto something, put it onto a platform and find the usefulness of it. And so partners like Scott and folks like that are great avenues to kind of work with, to kind of help push these new really technologies that we're thinking about and the group here in the ecosystem is really thinking about as being viable. Like Dr. Lewis said, if you have an idea, if you don't tell us about it, we don't know about it, right? And we don't know that we can use it, and we don't know how we can apply that potentially to some sort of product or capability. And so, without further ado, Scott, would like to have you come up here and talk for your section. Thank you.
Thank you all. Farhan, thank you for having me today especially, and also thank you for asking us not to focus too long on our configurations, because as you know, Bell hasn't revealed those ours yet. And Mark likes to razz me about it all the time, so I thought, well, tomorrow after Farhan asked me to talk more about the students, the university, and what our challenges were, that'll be a nice relief. So it's great to be here. Quick couple slides on just who we are. The Bell Innovation Team is a rebirth of innovation at Bell, an advanced concepts team. Not trying to claim newness. Bell's been innovating for a long time. It's just a matter of continuing that legacy into the future and looking at these new types of vehicles like eVTOL, for example. weaving in the ask today, I thought about, listing out specifics. I have a talk that kind of talks about how we are and what we look at in innovation. I think it matches what Farhan and everyone here wanted to talk about, which was, what are the tough challenges when you get into larger VTOL? Where are the places we can collaborate? What strategic decisions have we made? Where's the help needed, and maybe what have we missed? So it's going to be threaded out throughout my presentation. These are the things that we look at on the innovation team. They are familiar to most in the VTOL industry. I'll point out a couple that I think are great opportunities for collaboration. Our generic test cells that we have, one each in autonomy, alternate propulsion, and advanced anti-torque, are great ways that we let our engineers out of their offices and down into the labs to bring their great ideas to life. And I think that's a spirit that I see here at Rensselaer in the MOVE Center. I think that'd be a great place for us to work together. These are the tactical frameworks that we take those strategic technologies and place them inside of. I think I'll probably talk about energy management a little bit more today. And of course, the sensors, big data, and AI that are the backbone of autonomy. And really, you can't have a good autonomous system without those. So at Bell, on-demand mobility is, to us, a people-moving enterprise and also a thing-moving enterprise. So you have Bell partnered with Uber on the Elevate project, but there are other manifestations of on-demand mobility for people moving. Folks like Blade do it with traditional helicopters. This was our cabin mock-up that we revealed last year at CES. We did it without the flying bits in a way to reach out to folks that aren't familiar with VTOL and get them experienced with what it might feel like to take a vehicle like this on their daily commute. These are folks that we wanted to embrace at a different kind of conference and make sure they understood that they were the target customers for this future that we're trying to create. On the logistics side, we look at it both from a commercial standpoint and of course also from the military standpoint. We found a lot of commonality as we started to think about our vehicle, the size of the vehicle, the capability. Turns out that sweet spot in the middle of unmanned logistics support to the military and the distribution centers of many of these logistics players are all about the same distance, and they like packages of all about the same size. So we found some commonality there. This is APT. It's a vehicle that we are creating in a family. It's a tail-sitting biplane, very modular in terms of payload, agnostic to propulsion as well. And I think you've seen some videos out there on YouTube of this flying around, trying to address that small, medium, and perhaps even that large unmanned logistics support mission with this vehicle. Bell always thought, well, we'll stay on the high end of it. That's what we do best, but it's turning out that a 55-pound vehicle that can carry 20-ish so pounds and even a 250-pound vehicle carrying around 70 pounds is quite useful for a lot of commercial and military customers. And it's also a great way for us to introduce the product to those folks. I think these are really the challenges. These were mentioned in different ways yesterday, particularly from Steve, and I think you'll find I'm somewhere in between Steve and Mark, just in the fact that we've decided to work the problem. I think both make great points about the potential and the realism that need to be brought to this new adventure that we're all on. And really, technology is what we always focus on, but operations, certain manufacturing probably pose more challenges for eVTOL to really make it operational. I'll take you through a couple of those. On the operational side, the way we're going to address those challenges is we're partaking in the NASA SIO program with APT, actually APT 70, a 250-pound vehicle with a 70-pound payload. And we've laid out 3 missions: offshore logistics, emergency response, and then transport of tissue, blood, and organs. And we really don't want to do this on paper anymore. NASA and the FAA are partnering with us, and we'd like to fly in those environments. So where are the opportunities? How about beyond visual line of sight? How about flying in an airspace that's quite crowded right around the the DFW airport. And what does it take to do that? It's one thing for us to go to our remote site and prove to everyone we can move 70 pounds from one point to another, but it's another thing to have the sensors and AI on board to deal with contingencies, to find landing zones in these areas, to find the right folks that need help in that disaster area, and then to understand even how to do man-unmanned teaming out in some place like the Gulf where oil platforms are and they need service at many different levels. Certification challenges, I think it's an interesting point to talk about with university folks. And it goes back to one of the themes I've heard about today and this week, transition. How do we transition our research and development into certified technology? That's a big challenge. It's great to think about technologies in the lab and even in demonstration vehicles, but the point of industry is to get these vehicles certified and operational for our customers. And then meeting early and often is really a theme that we're trying to live by with the FAA and the other regulatory agencies. Manufacturing challenges, they're amazing. You know, I put a picture of a 206 there, and there's a big hub, a complex mechanical transmission, and a thermal engine. And if eVTOL lives up to its potential, those core competencies at Bell and other companies may very well change. Now, big hubs, mechanical transmissions, and thermal engines, they're not going anywhere anytime soon. The physics tells us that. But the opportunities are there in eVTOL, and those are the kinds of things we need to think about as we transform not only our own companies, but universities and the skill sets that the students have in order to think about what the future core capabilities at companies like ours are. So in terms of a couple things to think about along the line of Farhan's questions, you know, what are the big technical challenges in large eVTOLs? And I loved how he put together big and large, because that's the, you know, those are where things get really tough. I wanted to say wait, but I'll just say it once, and I think everybody knows that it's critically important here when you're power challenged. And then scale to cert, I'll call it that. Scaling is a wonderful thing, and the subscale models that we can now build, given the capabilities out there with control and electric propulsion, are wonderful things to experiment with, and we should do that. But let's ask ourselves, how do we scale to cert? Not even scale to demonstration, but scale to cert in the system safety, integration, and all of the things that you have to think about. Steve talked about those a lot yesterday. Energy management, very big for us. This is external or internal system energies that aren't being used to do useful work. What do we do with them? Can we convert them? Can we attenuate them? Can we move them to places we want them to be in? And I categorize it in thermal management of eVTOL systems. That's a big one we should look at together. Noise, you know, you go to electric distributed propulsion or more electric distributed propulsion, you can deal with that. And then auto rotation, people don't think about it in terms of energy management, although we should. And it's a big question for distributed systems with smaller hubs. Bell's not big into parachutes. I can't imagine an aircraft coming down like that in the middle of New York City, let alone with our name on it. So we are going to find an energy management type solution to that problem of or lack of auto rotation. And then system safety and the mission itself. These are kind of cascading, right? So you need the great situational awareness and autonomy to be safe and accomplish your mission. That's the business case unlocking when you take that pilot out and put another paying customer in a 4+1 vehicle. But you have to have the situational awareness and those non-deterministic software algorithms in the autonomous system to only do those two things, really. It's not important for much else, because safety and mission are what we're trying to achieve. Farhan asked, you know, what are our differentiating decisions that we made strategically at Bell? So we're not alone in any of these, but we're going for 4+1. The +1 means start off with a pilot initially, and then eventually transition to a fully autonomous system with 4 to 5 passengers. We like the 800 to 1,000 pounds. In the logistics, it also happens to match 4 to 5 passengers at 200 pounds each, and that looks like the right place to really support folks doing logistics missions. It's not about dropping soccer sneakers off in people's backyards to us. It's about supporting distribution centers for commercial customers or supporting the great missions that the warfighter has, where the logistics chain is probably one of the most important things that needs to be attached and sustained at all times. We're also doing hybrid propulsion. I think you've seen that announcement from us. We're partnered with Safran using hybrid propulsion to bring our eVTOL vehicle about. It's tending towards a 6,000-pound vehicle. Hybrid propulsion to us is what gives us a broader mission capability set. It's a range extender. Turns out it doesn't fix the weight problems as much as you'd like it to, and that's okay. We believe taking that struggle either way, all electric or with hybrid, is worth having for the longer mission. And if you can get your empty weight down, you can just add more fuel and extend that mission set. And then also the community and customer acceptance. I think we're trying to take a different approach here. That's why you saw us at CES. We need a new set of customers to speak to. And then we also use this mentality to address the question of requirements. We know that everyone doesn't have a perfect set of requirements, but if you can co-create with your customers, that's the answer. It's not telling your customers what you know and you think they don't know. It's about co-creating, about anticipating their unarticulated needs, and that's how you get the best system. Great collaborative areas here. I wrote down adaptive geometries before I knew about all the great adaptive geometry projects the students here have, so I was really excited to see that yesterday out in the lab. I saw a lot for edgewise flight, so difference between hover and cruise. I'd love that to be applied to powered lift, so the difference between edgewise flight and wingborne flight. We need two different geometries there, whether in the hub or other supporting structures. Integrated technologies. I need a single machine for my hybrid vehicle, a single piece of turbo machinery, not a turbo shaft, gearbox, and a generator. That's a big deal for us. Also, integrated technologies in power electronics, battery storage. Can it be a part of the structure? Are you putting your sensors and your management systems into your motors and battery packs? How those things become more integrated. Because as they're separated and struggling to be power dense or energy dense, it just compounds itself. They need to come together and answer that weight question for us. And then I'd like to ask that everyone work on the digital fabric together. It's a lot of fun to have a digital fabric that ties your CAD to your manufacturing, but it can't stop there. That digital fabric has to travel out to the end user so that advanced health system monitoring prognostics can be used to bring our direct operating costs down and really serve the customer in a way that they understand how that vehicle operates. And then maybe what's missing? What are we not looking at? I think we need to be more honest about the well-to-wing environmental considerations. If you don't treat your batteries right and you're recycling those all the time, what does that mean? Where are you getting the electricity from in the first place to recharge them? I think there are some alternate propulsion opportunities out there on the horizon that we should all be looking at. I think the cost models and the business case, they continue to build, but they need some more specificity. And there's a lot of great opportunity out there. You have to go and meet individual customers in different parts of the world to know what the real business case is. And I think that deserves a closer look. And also the cost model, I'd like people to value their time and tell me then what I can do with the cost model rather than kind of arbitrarily setting a line comparatively to what we do today for transport. And then just on the safety side, I'd like everybody to just be careful about the difference between redundancy and reliability. One is a means to an end and one is the end. The reliability is the most important part, and we can do it without redundancy or with, and the same principles apply either way. And we need to put the hours on the components that we plan to use in these new vehicles. I'm going to close with a quick video if I could, and it's a video of a scaled vehicle. It's a tail-sitting ring wing called Hydra that we played with for a little bit, and I'm leaving this video in to encourage the students here to continue to play at the subscale. Remember what it is you learned there. It's not everything, There are certain things you'll learn, but it's certainly fun, and it's certainly a way to express your ideas in a physical format to impress the folks that fund centers like you're about to be a part of. So I'd like to encourage everyone to do that. I tried to do that on the innovation team as well. So this is always the moment of truth from all technology.
Thank you, Scott. Great talk. One point of note, I didn't note before, but we're gonna have our 6 speakers come up, and then after that, if you can hold any questions that you have until they're all done, we can have the moderated panel session. We can ask them all the questions we'd like at the end of their discussions. So next up, Mr. Chris Jaran, CEO from Terrafugia. Chris, as you know, is a distinguished alumni here of RPI. He's had over 30 years experience in the technology and transport business. Over the course of his career, he served in a number of roles and increasing responsibilities, ranging from overseeing the development of major aircraft design to establishing operations and leading corporations into new markets. Most recently, Chris served as Vice President and Managing Director at Bell Helicopter, where his overall responsibility for the company's operations in China. Prior to this, he was Operations and Implementation Team Lead at the Virginia-based Tetra Tech AMT, where he was involved in the Federal Aviation Authority transition to integrate ground and space-based navigation systems and its modernization initiatives. Before joining Tetra Tech, Chris spent more than 25 years at various subsidiaries of Sikorsky Aircraft, including Chief Operations Officer, President, and General Manager. So without further ado, I'd like to welcome Mr. Chris Jaran. Thank you.
Thanks, everyone. Let me first start by saying I think this is a terrific start for MOVE. Even my small company has committed to contribute to the funding of several research projects here, and I encourage everyone in the audience to do that as well. My little company can do it. I'm sure the big guys can do it too. Sikorsky, Bell, Boeing, right? I think this is something that behooves us to support, right? This is the place where things are going to start to. This is the place where things are going to start to happen. Sorry. I'm going to start with a little bit of history of our company, since we're new to the business in some senses. I want you to understand just for a couple of minutes what our lineage is. Terrafugia started about a dozen years ago by 5 MIT grads. Guys in grad school entered a competition. They designed a flying car. They won the competition, and they decided to form a company. That company moved along at a relatively slow pace for the next 11 years, struggling for funding and maintaining a pretty low profile and a pretty small number of people. They had a number of successes. They built some prototype aircraft. They actually flew flying cars. They made 2 different versions of a prototype vehicle. So they were somewhat successful, but struggled hard with fundraising. Last year in October, we were acquired by Geely. And Geely is probably not a well-known name in our circles in the United States, but it's the largest manufacturer of automobiles in China. So it's really a multinational giant that's been in business for about 30 years. They own a number of different companies. They've acquired us, obviously, but they also acquired Volvo. In 2010, they acquired a failing car company in Sweden and turned it around to the point where last year they delivered 650,000 cars worldwide. Right? They purchased the London taxi company, the iconic black cab, and they've turned it into an electric vehicle, and it's now in more than 50 countries. They acquired Lotus Cars, the manufacturer of high-tech sports cars, actually all composite, very lightweight, very fast, and they're about to introduce a couple of versions of SUVs this year, expanding their business base. They just purchased half of the largest car company in Malaysia. I think most recently they acquired 10% of Daimler, the Mercedes-Benz company. Right? So this is a company that's large, that's global, and really has changed the landscape for Terrafugia. I joined the company only about 18 months ago, and I can tell you that July 1st last year we had 19 employees. Right? It was basically the core folks that had been with the business for a long time through the ups and downs that were still supporting the project. Today I have 240 people, and we continue to grow at the rate of about 5 staff per week, and that's what we've been doing for the last year. So here's a pause for our RPI grads, right? I employ co-ops and interns. I think it's a terrific thing for us to do. We do it year-round. This summer I had a dozen, right? And we're just now transitioning to the new term, right? So we have 10 more people who are in our shop in Boston. I have 2 of them in our California office. When I began, we just had a small office in Woburn, Mass, about 12 miles north of Boston. As I say, most of our staff was there. Today, we're at about 125, predominantly engineering, but it's also the center where we build full-scale prototypes. We have all the facilities to make composite parts, to do assemblies. I've expanded that facility 3 times in the last year. And actually, it's not on this slide, but I just opened up a flight test center about 30 miles north in Nashua, New Hampshire. Right? We've leased the hangar space, we've renovated it, and that's where all of our developmental testing will happen, as well as our acceptance testing for our production vehicles. So we've added a 4th facility that's right now very small staff, but will grow quickly as we start to deliver product next year. In Petaluma, California, which is about an hour north of San Francisco, we have our R&D center. Right? We opened that up early this year. There's now about 20 staff there. That will grow to probably be double that next year. That's our conceptual design center. That's where all of the new design products begin, right? We run through lots and lots of iterations, as you would in any big company, right? That's where I started with Sikorsky, and we used to call it advanced design, but it was the same. It was the conceptual design group. We dreamed up a new design every month. We threw away almost all of them, but eventually some of them went to production, right? They went on. We flew them. Some cases we went and started building them and putting them out with customers. That's my Petaluma office, right? It's a small center, but they have the capability to build scale model flying prototypes up to about 1/5 scale. They have a full shop. They have a 5-axis NC machine. They have a full composite shop. They have NC ply cutters. They do all of the things that we do in the big shop in miniature, right? So we able to test our products at a scale. And when we identify successful products, then we bring it to our Boston office and start to build full-scale ones. And I've opened up an office in China. Our parent company is in China, and that's where we do all of our manufacturing, our production manufacturing. Right? So I've grown from 0 to 96 people is the number we had last week, and they're growing fast. And they're producing production parts for our first product right now. Right? That group has started from nothing, and we're making composite parts and assemblies of those that will be on right now they're on our next generation of prototype vehicles, and they will be the sole source supply for all of our production vehicles. Final assembly will happen in the United States in our Boston office, but parts production happens in China. Okay. I guess it's important to note our initial product is a bit different from the eVTOLs that we've been talking about, and that's as a result of having worked for a dozen years on that product. Right, we're able to bring that to market fairly quickly. It's a two-seat light sport aircraft that's certified by the National Highway Safety Transportation Authority and by the FAA. So we have the approval to drive it on the highways, put a license plate on it in any state in the union, and to fly it from any airport or grass strip if we wish. We've had our first prototype flying for a couple of years, and we're actually now finishing the next prototype, which upgrades a lot of the systems that we've been able to develop over the last year. So it's road legal, and we'll be delivering those next year. Right? Our target is to start putting those in people's hands next year, and we're right on schedule to do that. Right? As I said, parts production is underway, testing is underway. We ran our first crash test of the automobile a couple of weeks ago. Right? It was very successful. A lot of parts failed. Right? Crumpled beams worked, the safety cage that's around the passengers worked. In effect, everything functioned correctly, and now we're back to clean up some of the design to make it a bit better. The next generation product we call TF2 for lack of a better name. We haven't really named it yet. It's Terrafugia number 2, and it is an air taxi. It's similar to what the gentleman from Bell talked about. It's a 4-passenger vehicle with a pilot. A commercial pilot operates the vehicle, and it's also a cargo aircraft, and I'll show you that a depiction of that in a minute. That aircraft we're envisioning will be in the market in 2023. Next year, I'll build a full-scale flying prototype of it. By the end of next year, we'll be flying that vehicle in full scale. So we're in a mode to go very fast, and that's really the gist of our current company configuration. Right? We're creating an air vehicle company. We're not just one of these companies that's creating one eVTOL and has no future concepts. Every 3 years, we're going to produce a new vehicle. Right? We're going to become, in effect, a car company in the flying car space. Right? That's the projection, and that's what's been fully funded by our mother company. Right? They've agreed to a 10-year plan for us that fully funds us for that period of time to do these kinds of developments. Just one slide about our first product, 2-seat, roadable, certified for ground and air, 1,400-foot runway distance. And really the beauty of this product is you put it in your garage, it fits. You drive it to the airport, you unfold the wings, you fly where you want to go, you fold them up, you drive to your destination. And when it's time to go home, you turn around and do it the other way. It's in the same price category as a Cessna 172, except you don't need a car to get to the airport, a hangar to store your aircraft, a rental car at the other end, any of those things. So it's effectively something that enables you to operate more efficiently. And here's a quick video that just shows you, this is the second prototype of our vehicle that's been flying for a couple of years. So the obvious question is, if we're talking about eVTOLs, why is my company focusing on that little aircraft that requires a runway, right? And the answer is, it's a way for us to develop our business. Right? I have to go from virtually no staff to a fully operational aircraft production company in a very short period of time. By taking the product that we had already started and building on that, I'm able to complete the production design of an air vehicle very quickly. I build my team, we prove out our systems and our operations, and I can demonstrate to the public that we can put a certified vehicle through our engineering process in a year, basically. Once that's done, I go right to production, and I'm able to prove to the public that I can deliver a certified, safe flying vehicle within the following year. Right? So all of that lays the groundwork for what's coming next. And that's admittedly a fairly small market. Cessna sells about 100 172s a year and have for the last 10 years. It's been in production for much longer, but that's been the history. Cirrus sells about 120 SR-22s a year, right? So that's the market that that product's going to be in. But the next generation is much different, and that's what Mark Moore was talking about yesterday. He said 10,000 vehicles a year, right? It's absolutely incredible, right? It's remarkable where we are in the development of products as compared to anything in my history, right? I graduated from here in 1978. There's never been a time like this, right? In 25 years at Sikorsky, I saw a couple of vehicles produced. My company has produced 2 vehicle designs in the past 2 years, right? It's remarkable. It's disruptive technology, right? It's the most exciting thing that you can imagine is what's going on today. So I'm going to show you just a couple of slides about our next generation product, the TF2, right? Said it's a single pilot vehicle, but it has all the capabilities to be autonomous, right? Most of those exist today. I was proving that out when I was with the FAA, right? Fully automated flight is entirely possible and being used all the time. So we put that in the vehicle, but we have a pilot. And as we build hours and we build experience, we can transition to just going pilotless. But in order to get into the market quickly, you need to put that commercial pilot in. We've developed a cabin that carries 4 passengers and separates from that air vehicle. And I'll show you a quick video that shows you how that works. And a ground vehicle, which is a simple pickup truck kind of affair, right? Something that my parent company makes hundreds of thousands every year. So that's the simplest part of the project. So sorry, this one doesn't have beautiful music, but it shows you the concept, right? So again, this is similar to our first product, it's door-to-door transportation. The ground vehicle with the passenger compartment picks you up wherever you call it on your cell phone, and it loads to our air vehicle. And the air vehicle is a simple product with fixed pitch propellers in the current configuration, with a wing, to answer Steve Weiner's question, to get you into wing-borne flight quickly, because that's more efficient when we're trying to fly distances that we think are on the order of 50 miles for many of our missions. We try to fly with our rotor system and electric power system as infrequently as possible. But basically the entire vehicle is electric, right? In this case, we have a gas turbine engine that generates energy. We have a battery pack that stores the energy. And then everything else is electric. The lifting rotors are electric motors. The propulsor is electric motor, right? So in the future, we're able to swap that out. When battery technology arrives that allows us to do our mission, and here we are, so the container was picked up by the ground transport and delivered the passenger to their place of business. So we've designed the vehicle so that we can go into production immediately and put it in service immediately. We don't have the issues with only electric, only battery power. That gives you a very limited ability to fly. Right? Today's battery technology is going to give you about 20 minutes of flight time. And unfortunately, the FAA requirements today say you need 20 minutes of reserves. So it's kind of a non-starter. So for us, both of our products currently have hybrid engine systems. Right? In the future, when the batteries develop, and we think they will, we'll pull the motors and go to all battery-powered operations. So for us, this is a very simple concept. It's much like the containers you see all over the world, the big boxes. We can make them into anything we want. They can easily be transformed into medevac systems or anything that we want, offshore delivery systems, right? But fundamentally for us, passenger systems in the US, cargo systems to a lesser extent here, but in China, where our home company is, it's an enormous business, right? Brick and mortar stores are a thing of the past. They're really all disappearing. Everybody orders everything online. And today it's delivered by airliners from airport to airport and trucks into cities and even motor scooters to people's homes. So the big outfits in China that are doing that, SF and JD are the 2 biggest, are very interested in us taking the trucks out of the equation, right? Moving faster, moving over traffic, which is really the idea behind all of this. As I say, for us, the roadmap is 2023, the next product, 2026, the one after that, and you see every 3 or 4 years another product. In fact, my research group is going to start on the next one, TF3, at the end of this year. So we're in a development cycle already to create a permanent flying car company. We were asked to talk a little bit about challenges, and I'm going to just run through these pretty quick. I mentioned already batteries, right? My company owns battery companies, and they're producing for electric cars today. The Geely company produces a number of all-electric cars. They produce a large number of hybrid electric cars. Well, the Volvo company is going all-electric in 2020. They won't produce anything that's not all-electric. So we understand the battery technology at a corporate level, and we understand that we can't go there right now, but that it's sort of like what happened with semiconductors, with Moore's Law. The battery technology is improving fairly rapidly. So we think it's not that far in the future, 5 years perhaps, before we're able to do that. Electric motors are another challenge. The companies that produce electric motors are not ready for the onslaught of 10,000 vehicles. And if you look at our products, there are 4 rotors, there are 4 electric motors, there are 8 electric motors. I can tell you that Siemens is no way envisioning making 800,000 electric motors a year, right? So we're investing in that technology with some smaller companies who are developing prototypes for us. We see that as right now a showstopper. Can't produce enough, and certainly you can't produce them at the proper power levels. And I think the guys in the room know that's historically a problem with aviation. You got to have the motor before you have the vehicle, or you fail, right? Tell us about the 76A program, right? And what happened with the Allison engines, right? That we pushed too hard. Tell us about any product. Tell us about anything in the past when you overstep the bounds of the propulsion system with the motors that are available. So we're investing in that and working close with a couple of smaller companies that are developing prototypes for us, and we'll actually be running those by the end of the year. Flight control system's another big problem. I don't know that any of us really thoroughly understand how to operate a quad rotor, a hexarotor, a lifting rotor system that transitions with propulsors into forward flight. What's that flight control system look like? What are we doing? I can't have passengers going ballistic, right? I can't do those kinds of things that you can with a UAV or with a drone. Right? So I need something that we create that doesn't exist today. So that's a big step for any of the companies. Multi-rotor propulsor systems, that's the same issue, right? How do we integrate simplicity into our systems? So we talked about we want to have rotors that have cyclic, we want to have rotors that have collective, right? Well, we want to have a rotor that's a club prop that has no controls except for RPM, right? Because that gets you to absolutely the simplest design you can have, gives you the highest reliability you can have, and we do some unique things to put the control system into that by varying RPM. Vehicle certification, here's some things that I don't think many people have really addressed. How are we going to certify these products? The FAA doesn't have a category for them today. How do you certify the multi-rotor pusher prop vehicle? Well, we actually have a team of people in our company that have helped to rewrite Part 23, the certifying document, right? So for us, that's how we certify with the new Part 23, and that means it has to be fundamentally a wing-borne flight for part of the operation, and we do that, right? So I think that's where we really need to have some concentration. I encourage the guys here to get involved in that, right? Why don't we get the business group at RPI involved in working with the FAA, crossing over between the technical guys and the business folks, the business development folks, to talk about how do we certify the products, and even more than that, how do we deal with air traffic control, right? The single biggest problem we had developing the precision approach systems, the precision routes for the FAA was ATC. They are in no way prepared to take 1,000 operations an hour at any vertiport, right? These are guys who today like to have 90-second separation between operations at an airport. They're not ready to do this stuff, right? It's another opportunity here, I think. Get our people here involved in working together with air traffic control, with the FAA, to rewrite those regs and to get acceptable operations here. Otherwise, everything stops. If air traffic says you can't fly, we're dead, right? Those 10,000 aircraft sit on the ground. Finally, Mark yesterday mentioned about pilots. This is incredibly difficult. There's not enough commercial pilots in any area. helicopter, fixed wing, commercial airlines today to support what we need, right? I know in China, where I've been for many years, they're sucking them up out everywhere, right? We need a way to make commercial type pilots faster. One thing you do is simplify the operation of the vehicle, right? And that leads to simplifying the certifying process for the pilots, right? Make them faster. Today it takes a year to make a commercial pilot and it costs a ton of money. How do you do that in high speed? You fix the vehicle and then you fix the system. Okay, so afterwards, anybody wants to talk to me about co-ops, come see me. We're wide open. We have, while we're a small company, we like to encourage that stuff. So thanks very much.
Thank you, Chris. Great talk. Our next speaker, Mr. Matt Ciuca. He's from Aurora. He's been there since 2016. He works as a director of strategic and commercial programs. He's responsible for developing analytics and recommendations and strategies for business sector leaders with commercially focused programs. Mr. Ciuca has over 11 years of experience in leading business transformation, market adjacency, acquisition, due diligence, and strategy projects within the aerospace community. He holds a BS in mechanical engineering from Clemson University and an MBA from Carnegie Mellon Tepper School of Business. So without further ado, I'd like to welcome Matt to the podium. Thank you.
All right, great. Well, thank you, everyone, and thank you, Professor Gandhi, for having Aurora as part of this. You're going to hear a lot of the same messages, I think, as we go through. But one of the things that we talked about that a lot of people said is this is a new and exciting area for everybody entering this market at this time. And so one of the things that I wanted to show was, there's few times in history where there's really a new hit product. And you really have to, outside of the small drones in the last decade, you really have to look back several decades for that last hit product. And so this industry is new for everyone. So I wanted to touch on some of the key development challenges that we're thinking about at Aurora. And these are not different than I think what you've heard on the last presentations. But so Scott said, wait. I put that as the number one there, is keeping the weight down and understanding what systems we can put on. And then second, attaining the passenger safety levels. So I think that's been a common theme throughout many of the presentations yesterday and today, and also several of the technology challenges. And then it ties back into the weight because we need a lot of systems for this level of safety. Battery, energy density, performance, and thermal management. A lot of folks have talked about that. And decreasing the acoustic signature, so the environment, whether the communities are going to accept it, whether the riders are going to accept going on the vehicles, and so that's really going to drive that market acceptability. The next one is enabling the asset to operate with a high utilization factor. So a lot of discussion on the pilot shortages. You've heard that. There's been a lot of discussion on the fact that we need these to operate much more volume at airports than our current air traffic does, and many more in the skies than we would currently have. And then lastly, the high rate production. So the quantities that we're talking about is different than we have in aerospace today. And so we're thinking about that on the front end rather than after the product is developed and certified. And so we're really thinking about that from the beginning. And from Aurora's perspective, autonomy is really the key to this, to many of these. So I'm going to talk a lot more about that. There we go. So I'll just say a couple things. So what's enabled us to come to this point is lightweight electronics and powerful electric motors are really enabling all these new configurations. And you can see a couple of Auroras there. You have the Lightning Strike on the top. You have a vehicle there in the middle that was a military vehicle that had vertical capabilities. And then lastly, you see our eVTOL demonstrator, the subscale that I think everybody's seen in some of the Uber Elevate presentations. And then, I know a lot of people have talked about the battery technology. We do think, though, that the batteries give us a reasonable range today, but as a lot of people have described, it doesn't give you the full range of where you can go. But I put a map here about where we can get in 2018 and then where we can get in 2025 with battery technology, and I centered it here where we're sitting today. So for those that know the area, you can see what markets that would open up if you were to go outside and get in your eVTOL when the market first comes out. So that's what I said. I'm going to speak a lot more about the autonomy side of things today. But one of the things that we wanted to show, everybody's talked about the pilot shortages, and I think it's important. Mark Moore yesterday talked about specifically the helicopter commercial pilots. These are graphs of the overall pilots, so this would have fixed wing and rotorcraft in it. But you can see that while the ATP pilots have been increasing, the commercial pilots have been dropping for several decades. And several technologies have come out over this time, that were promises to simplify the operations, to bring more pilots into the fold, into the, I'll say more potentially the GA community, and then to really improve access to on-demand air transportation. I remember quite a bit of talk in like the 2005 to 2007 timeframe when the very light jets were coming out, and several years after Cirrus had entered the market, there was a lot of talk about this on-demand aviation using those higher-end single-engine propeller aircraft and then the very light jets, but we have not seen that happen. Then if you look in the last couple years, the amount of drone pilots have really drastically, it's a significantly higher number than any of these pilots. And the question is, what disrupted this? Why are there so many drone pilots when there's not other pilots? And so it really comes to the autonomy, to the ease of use. We've simplified it to where anybody can walk out, take the drone out of the box, and start to fly it, right? You don't have to read through the manual, you don't have to go through several months of courses, but you can take, there's rules. Yeah, there's rules. You can't go to a certain height. You can't fly in certain locations. So you have to know some of that, and there is the Part 107 licenses for commercial use, but it's really simplified it to where anybody can go and fly that aircraft. And when you really think about it, so aviation currently, we're in the age of amateur radios, where actually your pilot's license gives you the right to operate on those airways. But as soon as you go over the line into Canada or down into other countries, south of us, you actually have to go get your radio license to fly your aircraft. And the FCC governs that. But what we've talked about is, in the age of iPhones, we all walk around with our radio on us and we all operate it. We did not get special training to operate it, to talk to the different cell towers. We use it, and that's where we want to get with the aviation and the controls of these aircrafts. So a little bit about what Aurora is doing in this aviation area. So we've been developing these autonomous systems for actually 30 years, and several of the systems that I've talked about and will talk about are here on the left, and then just some general stats about Aurora. We have 8 locations, 4 primary locations here in the U.S., and then and a large facility over in Switzerland, and then some satellite locations in addition to that. Like I said, we've been closing in on 30 years here. We have over 30 UAS designs. You can see in the news our Orion product. We have 80 hours in the air on that product, so not only autonomous systems, but high endurance systems. And then we've gone to 103,000 feet with our autonomous systems. So I'm going to show a quick video.
Helicopter that flew in the Vietnam War, but now it's equipped with a high-tech autopilot system. The helicopter flight is controlled by a Marine on the ground using a tablet. He says it's easy.
Order an Uber, order a pizza. That simple.
Sergeant Deontay Jones says he doesn't know much about flying a helicopter, but he says it didn't take much training to accomplish this mission.
Basically the same thing as calling an Uber. All you're going to go do is submit a new request, and you just press submit, and you're good to go. It comes right to you with the supplies that you need.
So this was a project that Aurora had worked on for the Office of Naval Research, and the whole idea was to take and automate an existing platform to the point that anybody could fly it with literally minutes worth of training. So they, you didn't know who was going to be the operator that day. You didn't know, and you had only minutes to train them what they were going to do. So the use of the, he talked about the iPad and it being like an Uber, but it had to be self-intuitive for them to be able to apply the commands and request the information. And this was, like I said, it was for the Office of Naval Research, and it was about a $100 million program. So a lot of people have talked about the pilot shortage and the automation, and we think the automation comes both from allowing for these vehicles to be used in the scale, basically allowing for this limited population of pilots, but also for the safety. But when you step back and think about what does the pilot do in here, we aviate, we navigate, and we communicate. And the aviate, we're actually flying the aircraft. We're doing everything that's in the pilot's operating handbook. That can be all of the normal operating procedures, but that's also the emergency procedures. So managing the contingencies, and then we're monitoring what the aircraft is doing, and we're evaluating the weather and having to potentially change course, et cetera. Second thing is navigating. So now that we've flown the aircraft, and any good instructor is going to tell you these three things in this order. You aviate first, then you navigate, you figure out where you're going, and obviously you don't run into stuff. And then you also have to be aware of the airspaces and what you are. And then lastly, communicating. And so that's talking to other pilots in the air, talking to ATC, getting your clearance, et cetera. So I'm going to kind of talk through each one of these. So the first is aviating. So a little bit about how Aurora is approaching this. So we actually have certified GA aircraft. So this is an example of a DA-42 where we've taken and put a robot on it, and the robot actually can fly the entire pilot's operating handbook. So everything that a pilot would do to maneuver this system, to check the systems, understand what the aircraft's doing, and do every maneuver that's per the pilot's operating handbook. We do that today on a certified GA aircraft, and it's actually a system that we can turn off and on, so you can actually jump in it and fly it under its certified certificate, and then you can actually turn it on and operate under an experimental certificate, and so it can be optionally piloted. So we'll fly with a pilot in it to a location, and then we can use the system. So the next one is also in the Aviate. This is a program called Elias, and it's actually a robotic system that's flying. This is a 737 simulator, and so John likes to talk about this as a robot flying a robot because it's actually flying the 737 system. Again, it does everything that's in the pilot's operating handbook. So then I'll jump to the next section, which is the navigate. So this is an example of the perception equipment that's actually on the ACUS system. So that was the first system that we saw the Marine actually ordering a delivery. And what this is it actually has to come in and evaluate the area and determine where to land, where to safe land. And then obviously today, a human operator will confirm that that's the appropriate place to land. But so you can see that we're already looking at the sensors and the software required to do the navigating part. Now, I didn't bring a slide on the communications side of things. I didn't bring anything to talk about the communication side, but we basically, even when these are operating autonomously, currently we relay our communications. So we talk to ATC. ATC doesn't know that there's not a person sitting in that aircraft the way that it's done. So what does that mean for? So I know there was a request to talk about the different concepts that the companies have. So what I wanted to show here was actually there's a range of concepts. And at Aurora we're thinking of it in many different ways. But to us, it's really about building that certifiable autonomy that's the backbone that can power any one of our eVTOL concepts or configurations. Because to us, it's the pilot shortage. It's the safety. There's been so many other presentations have touched on the safety, but I think we have to have these autonomous systems to get there from the safety aspect. And then it's the operation at the scale that we want to do to make this, this industry viable. And so that's really where I'm going to close out. But I appreciate you guys having us, and I look forward to the questions later.
Thank you, Matt. Our next speaker is Mr. Mike Duffy. He's a project manager at Boeing Research and Technology, working on programs like the Boeing Horizon X, as well as leading propulsion technologies for Boeing's cargo air vehicles. Has over 15 years of experience at Boeing, both in aerodynamics, propulsion, conceptual design, vehicle performance, and unmanned systems. He has a Master of Science in Aerospace from Georgia Tech and a bachelor's degree in aerospace from Penn State University. He also works as a part-time faculty or scientist at Cornell University, Department of Aerospace and Mechanical Engineering. So without further ado, I'd like to welcome Mr. Mike Duffy.
Well, first, I just want to thank Dr. Farhan Gandhi for inviting me. Very distinguished panel, so I feel like I'm very honored to be here. I'm also very happy for you and the center and the launch of the center. The work you're doing brings together the old rotorcraft crew and then all the new eVTOL folks, and I commented yesterday to you about that, and I still think it's really impressive how you're doing that. So, so thank you. I also want to thank Mark Moore. I don't know if he's even here anymore, but basically yesterday he talked about don't tell him the answer, tell him the journey. So really quickly I want to just say that my journey started in V-22, and I was an aero guy, and for 10 years we were working on lots of concepts and doing really cool things, and then sort of I was like, man, I really need to build something. And Coop will know this because in about 2012 we started Innovation Cell, and we're like, man, we got to go make something happen. So we came up with this idea called cooperative lift. And really the idea was just take a bunch of helicopters, put them together, lift something heavy. That helped you get new missions, new mission sets. But we actually started learning more about electric propulsion and distributed propulsion, and we started saying, hey, we should make smaller versions of this, and we looked at commercial markets. And so we went in my basement, we started building some things, some engineers and I off time, and then we actually got some videos out, and some CEOs and some folks were really excited about it, and Boeing gave us some more money. We actually demonstrated 200 pounds of lift, and it was like a year project, and I was all giddy and having a good time. And then 2014, hit the brakes. Like, whoa, Boeing's not ready for this. You guys are getting too real here. And the reason, I think, was because it was a little early. Okay, and we were just not quite ready yet to put the Boeing brand out there. And I was pretty upset. I went back to my day job in B-22, and I went back to Aero, which was a great job, by the way. But I think what I learned from that was that we were like the Netscape, actually, of before there was Netscape. We were like way too early. So bottom line is, I'm glad I stuck it out, because I'm about to show you some stuff that we're working on now, and I think this is really relevant to what's going on. And I also want to say that Aurora now is part of Boeing. I don't think you mentioned that, Matt, but I'm really glad to have Aurora because they move fast and they're really great, and autonomy is their expertise. So some really exciting stuff going on. I'm going to show you a quick video of what we're doing, and then I'll talk a little bit more detail about the challenges. So this is that's our latest vehicle. I'll talk more about that. And then here's some Aurora videos. So we're like this. And just for fun, we're going to throw a hypersonic transport in there. Why not, right? I guess first of all, I want to say that I want to hire a lot of RPI folks because you're already working on a lot of relevant stuff, and it'll be easier to get you going. So, of course, everyone here in the panel probably wants to hire you. So, I want to make sure this is the coolest job out of all of them. But you all sound like you have really great jobs, so it's going to be really rough. All right, stop. So the next slide is the key. Sorry. I'm in some weird mode. Hold on. Gotcha. Sorry. All right. So what's enabling all this? What's happening? What's changed between my story 5-6 years ago and today? Well, about 16 months ago, Boeing stood up an organization called Horizon X, and they are, and really the goal of why they even started it was because they're basically trying to find opportunities that Boeing business units would not pursue on their own, but which basically are strategically aligned with Boeing's, end goal, which is moving people around. So, and then they broke that up into 3 groups. There's ventures, and this is where you'll probably see a lot of news. We do a lot of investment in small companies, and I'm going to go over some of those investments and how that relates to this ecosystem. And then there's the disruptive horizons, which is like basically a group of people who are saying, strategy folks who are saying, how do we disrupt Boeing? So they're actually looking to disrupt ourselves. And then there's the business development, which ties it all together. It takes the disruption and the investments and says, hey, how do we actually make this have money out of this? So that's sort of like one of the big game changers, and I sort of clawed my way into this group. After 2 years of working in defense, this is mostly a commercial thing. We're not focused that much in defense in this organization. So the ecosystem, there's actually a really cool video on this, but you'll notice that this is a big, broad picture, and the real key thing about this is that we are not focused on just the air vehicle. In fact, the air vehicle is just a tiny little thing up at the top there. Aurora's vehicle's in there somewhere as well. And like Mark had said yesterday, it's really not just about the vehicle. It's going to be about how we do the UTM, how we do the safety, how do we do the manufacturing at scale, how do we get the value proposition in front of people? How do we start showing value right now? Can we get that done right now? Do we need to wait for 2 years, 3 years? Can we get something in front of someone now and get it done now? And I think that's sort of one of the cool things about this organization. And then one other piece of this is Horizon X is sort of a group of maybe like 50 folks who are kind of like strategy folks. And then we've just set up another organization called Next. Next is the folks that take what Horizon X is saying, here's what's possible, and we actually do it. We're going to make it possible. And the project I'm working on is called CAV, Cargo Air Vehicle, and we're focused primarily on moving goods right now. We're not moving people because Aurora's doing that. So we're sort of working in parallel in that sense. So some key investments I want to go over here, and there's been a lot announced, but some of the cool ones are Matternet. I don't know if you've heard of them. They've been around for quite a while. They're actually delivering medical goods right now in Switzerland, I think. And they're actually doing the end-to-end system. So they actually have the UTM worked out. They're working the actual delivery of it. So we're learning from them, and we are a strategic investment in them. KittyHawk.io, not Kitty Hawk like from the Google folks, but KittyHawk.io, which is focused on the actual airspace management. We have a software app that they actually go and they have. If you have a drone today, you can get this app. Helps you manage your airspace. This is stuff we're doing today, really happening. NEA, which is what you were showing, which is near Earth autonomy. They're focused on the last 50 feet. So what they're doing is they're automating the last 50 feet. That's the hard 50 feet, right? Right before you get to the landing zone, it tells you what's going on. Says, hey, this is a good landing zone. Oh no, there's a dude there. We're going to go somewhere else. And that's what NEA is doing. Spark Cognition is a company that's doing big data. So that's very nebulous, but you can imagine that's a good thing to have when we have all this data coming in. And then finally, one of the other big investments doing is Cuberg. Cuberg is a battery company that's actually got a new type of electrolyte that is going to give us 400 watt hours per kilogram at the cell level, but also manufacturability. They're from Stanford. So that's sort of like what, and basically the whole gist of this deal is we are trying to bring flight closer to the home. That's the goal. All right. So so this is to me, this is like really exciting. So I might show this video, I might not, but the basic gist is this. We built basically a 1,000-pound drone in 90 days. And the way we did it was we basically picked an end date. We said we're going to fly on this date and everything else is going to change. All the requirements are based around that. We'll even take the requirements down. We're going to meet the date. That was what we did. So we did. In June we started last year, and in October we flew the aircraft and we delivered that aircraft. We got it done. And it was a really exciting experience for me because I was a propulsion lead on this. So we had to find propulsion system in this class of vehicle. So that basically sized everything because like someone was saying earlier, propulsion's everything, right? What's available is basically what you're going to use. I think you were saying that. And actually, I'm going to play it because our CTO actually does talk in it. And I kind of want to show you that this is the thing that Boeing, we're committed to do this. Like this is happening. So I want to show this video. It's pretty good. and you'll see a handsome man sort of hang around the airplane often. Some of these times, it's really funny when you have a camera on you, and they're like, okay,
When I saw
act
it take
normal.
off, I was inspired
Yeah.
by it. This team of Boeing engineers was able to do the impossible and deliver a prototype.
In a matter of 3 months, we took a concept from a piece of paper all the way to a flying vehicle.
So this is an octocopter. It's fully electric on some Boeing custom designed batteries. The goal is to grow into a large-scale cargo platforms. If you extend the range and you extend the payload a little bit, when you think about delivering 250 to 500 pounds over a 10 or 20 mile radius, you can change the way that the world connects. You can change the way that we deliver goods.
We've really got a convergence of technologies right now in terms
That's
of
our
hybrid
CTO.
electric propulsion, vertical takeoff,
Not the guy on the
and
ground.
autonomy.
That was me.
That is going to unlock air travel in areas that we haven't seen it before.
So it becomes a test bed for future businesses, such as maybe a electrically vertical takeoff cargo. This is my dream job of trying to come up with something new that the industry doesn't have yet. So it's exciting.
The company really is trying to change the future of the world. They are driving and on the leading edge and pushing the envelope, but doing it in a smart way.
Boeing is at the cutting edge of technology in aerospace. We have a chance here to really change air travel, and we'll look back on this day as a first step in that journey.
I have chills right now. All right, so that's the big spiel, but I'm going to give you some realistic sort of things I learned from this project. So that was our first vehicle. We flew that last year. This year we started the second version of that vehicle, which is a picture there. You'll see it's called Cav as well. It's going to be a little bigger. It's going to have a little more capability. That's a prototype picture of it. We're not actually showing any public video, pictures of it right now, but we're taking what we learned in phase 1 and we're putting it into phase 2. Man, I'm going to give you some challenges I want you guys to work on around this space, but basically the test, learn, and fly is what we're doing. So we're learning a lot, and those are the things we're going to move into the next space. So it's the speed we're working at, it's the integration of all these pieces into the larger system, and that's kind of where I'm excited to work with you guys because there's a lot of technical challenges. I'm telling you, this is the most exciting time to be in aerospace. I'm 100% sure of that. So one of the challenges I'm going to give you, and this is just verbally, I didn't write it up there, is transition edgewise flight for rotorcraft, especially, and that's always been the challenge, is transition to forward flight. And cyclic loading, transients are going to be really a big driver. Okay, so think about that, especially when you're talking about stiff in-plane rotors. We've done it for many years, but now we're talking a much different scale. Heat. You gotta start figuring out how to do heat, because you don't just blow it out tailpipe anymore. It's like literally mass of heat that's just in the motors or in the batteries, and it doesn't get out easily. So there's technology around heat, getting the heat out. Flying over people. So the safety piece of this is one of the things that I actually wrote down as a Boeing advantage, is that we are going to do this 100% safe. There is not going to be failures because Boeing is not going to have a failure. So there's the brand part of it, but then that brand keeps us on track to make sure we're going to meet those requirements. And I want to thank Steve, because I think you really opened my eyes on how hard that will be when you start to have hundreds of thousands of vehicles. And that's not going to be an easy thing to do. And then, of course, help needed from this center is basically a lot of aeromechanic stuff. So I saw you guys doing rotor failures, rotor interference, acoustics. All those things are going to be very relevant in this new type of platform, rotor airframe, all those kind of things. So I can see you guys doing great work there. And I think the last advantage Boeing is going to bring to this, especially Horizon X, is that we are focused fully on commercial. So we had a discussion about how the rotorcraft industry was military and how that kind of slowed things down a lot. We're not doing that. We're doing commercial first, and then we'll take that product and we'll give it to the customer, and we'll either modify it for them later, that we will get there faster if we do commercial first. And we don't want ITAR. But thank you very much.
Excellent, thank you, Mike, great talk. Our second and last speaker, Dr. Rajneesh Singh, is from the Army Research Laboratory's Vehicle Technology Directorate. He serves as a team lead for the Vehicle Integrated Analysis Team, where he conducts research to enable highly maneuverable, high-speed, high-energy efficient platforms, ranging from small UAS all the way up to full-scale systems. This includes VTOL systems as well as fixed-wing platform mechanics, design analysis, flight dynamics, As a team lead, he's been doing a tremendous amount of work in terms of collaborating with external research partners. And lastly, he has one of the greatest bosses in this room, too. Thanks. No, thank you.
So, first of all, congratulations, Farhan. It's a great kickoff, and we look forward to working more with you. So, before I get into my presentation, I guess I should start with disclaimer that opinions I express are my own. Army is way too big for one person to talk for Army. And my opinion is that eVTOL, from Army perspective, has more relevance for unmanned operation, and especially given the scale where this technology is relevant at, I think at least in short, medium term, that's where it's going to find impact. So my presentation is really influenced by that opinion, and also the fact that how VTOL has such huge dependence on the scale. So those are the two guiding thoughts behind my perspective on this presentation. And the way I talk about is I have a few slides on organization, then some of things we are doing in this space, and an idea of how we could do things better to make more progress. So here is obligatory slide on organization. So ARL is Army's corporate research lab. Basic goal is to discover, innovate, transition technologies to translate basic ideas, basic science into actionable knowledge that we can transition to other organizations like Dr. Lewis's organization, and that ultimately finds ways into warfighters' hand. So as part of that goal, we have activities in different areas as shown here. And my organization or my activities are part of the Sciences of Maneuver, which focuses on basically vehicle technologies, and that includes ground air, and my group is focusing more on the air vehicle, going from a small scale all the way to large helicopters. Now, other part which is relevant to, I guess, move center or the goal of meeting here is this open campus initiative that ARL has recently started. And it has several elements, as you can read here, but it's really about a framework for more science and technology collaborations. And to answer some of the question, I guess a question that Mark, asked yesterday, how government is evolving to the new developments and faster developments in private industry. So how government is responding to that? So goal here is we have invested so much in developing resources. We want to open it up to outside world and outside collaborators. And as long as you are interested in working on solving Army's problem, we'll look forward to collaborate with you. So among the several elements here, the one I want to talk more about is this hub and spoke model. And part of that is the so-called ARL extended sites. So over the last few years, ARL has opened up these satellite campuses. The idea is that we want to reach out to resources or to capabilities which are geographically dispersed somewhere away from our core place, which is Aberdeen Proving Ground in Mid-Atlantic. So there are 4 centers right now, and the latest one to join that is ARL Northeast. And as the star shows on the right side, RPI is going to be part of that. And of that, I guess I should add that as ARL is trying to open up these satellite campuses, Farhan has done a good job in creating RPI Mid-Atlantic at Aberdeen Proving Ground. And this summer we had 4 of his students, and I assume they are all here. If you guys don't mind, I want you to introduce you to the rest of you. So JP is here, and all of these guys have been as good as exceeded our expectations. So we have been so impressed with the quality of work, not just the quality of work, but also the overall the culture that the intangibles that they bring in. So I think, Farhan, you are doing really excellent job in creating next generation of scientists or researchers that we may need to make advances here. So now let's move on to VTOL. I don't know how much I'm doing on time. Okay, so VTOL. So it's fairly clear to us that fixed wing is pretty boring. And this slide shows that. If you look at the scale of weight, going from 1 pound toy scale to large helicopters, fixed, you take wing, you take fuselage, you add engine, you get a platform. On VTOL side, even for range of at 1 pound, you have typical quadcopter configuration. at 30,000, which is Black Hawk scale or V-22 scale, is altogether different. And in this middle zone where eVTOL is going to be relevant at order of, I would say, 500 to say about 10,000 pounds in the upper range, that's basically big Wild West. I mean, in general, whole VTOL is big Wild West, but it's a lot worse in this area. So that leads to the challenge that I think, that word that captures the main technical challenges of VTOL, and the word that is scalability. It's really the scalability of different subsystem technologies. We can talk about aeromechanics. You take the rotor. On low scale, we have fixed pitch variable RPM rotor. On traditional rotorcraft, we have variable pitch. So similarly for propulsion systems. So the question is, do you scale up from the bottom, from the lower end, or do you scale down from the upper end? And where is that sweet spot of each technology? And that's really the critical technical challenge that the S&T community needs to address at. So that's one part. Now, second part that we need to understand is that on this side, we have history of over 80 years of developing S&T and developing products, and fairly good amount of knowledge exists. On this side is, I would say, maybe 10 years or maybe 20 years. Now, it's a mistake to think that vehicles in this space could be mini Black Hawk or mini Apache, or so it's an altogether different thing. So we need to be ready for out-of-box thinking. So sometimes the good knowledge that we have on the larger scale may in fact hurt us if we try to think within the same box of I would say art of possible of that for the large scale. So this is the least understood scale, and the cost of not understanding is also fairly big. On a smaller scale, you can always overpower your rotor that can hide away your design flaws, your lack of understanding. But that may not be the liberty we have at this scale. So we need to have good understanding of the underlying science. And at ARL, we are active in across the scale, ranging from Group 1. These are the DoD scales of how they, based on the weight of platforms. So ranging from Group 1 all the way to Group 4. And in the next 3 slides, I have examples from lower end to the large end, and how elements in those areas are relevant to eVTOL scales. So let me start with on the lower end. So the project here is about developing a design and manufacturing process that allows a warfighter to build a small quadcopter or a small UAS on demand. Based on the mission requirement, we want to create a process that mission requirement get translated into a vehicle design, and then using additive manufacturing could be assembled in matter of hours. So one critical piece that we need here from in addition to advances in additive manufacturing is having a tool that gives you the performance, or if you're designing certain vehicle to meet certain performance, we have to have good confidence in that. So we need, and again, because of scalabilities, with all the knowledge of large scale tools that we have for large helicopters, some of those are not applicable in this space. So the solution is that we probably have to look into bringing higher fidelity into our design tools. And as we are doing this, one of the things we are realizing is that models for electrical subsystems, motors or batteries, is one of the big gap. And so that's one interesting challenge for S&T community to work on. Now on the other end is this tilt rotor aeroelasticity. This is a project or effort that's focused more on the large scale for future vertical lift. So wall flutter instability rather, it's a well-known problem for tilt rotors, where the dynamics of rotor couple with dynamics of the wing, and that can lead to instabilities at high speed. And the way you overcome this is by designing a thicker wing that leads to weight penalty, that leads to performance penalty. So now we have effort on all 3 sides. So we are fabricating a test rig that would be available for internal test in 2020s. And this is also areas where we have collaboration going on with Scott's team. In fact, right now we have 3 of our colleagues sitting at Dallas who are discussing exactly the same project. So now again, tilt rotor is probably going to be fairly, I mean, it looks fairly promising candidate for eVTOL applications point of view. So some of things we are going to learn here, which will go into developing tools or just the basic knowledge itself, is going to be relevant for eVTOL applications. Now, third example, it's focused on group 2, group 3 scale, which is the prime eVTOL scale. And idea here is, again, to look at rotor concepts for this class of vehicle. So once again, because of scalability, there have been some concepts which have been looked for full-scale larger platforms, but have not found to be feasible. So there are some concepts which can make sense for this class. And the stacked co-rotating coaxial rotor is one of those. And on this topic, we do have collaboration with Uber, where they are paying for the experimentation part, and we are doing the modeling simulation part. And for experimentation, they have a separate arrangement with the University of Texas Austin. So again, goal here is to develop not just look at the new concepts, as well as developing the whole capability that we could use to investigate to develop new kind of rotor technologies. So other one that can be looked at is unequal spaced rotor blades. Again, this is technology that probably will not work at larger scale because of dynamics issues, but it can be at least explored more strongly for this scale. So this was just a small subsample of what we are doing. So in addition, we have efforts on flight dynamics, efforts on rotor interactions, and so on. And I think that's what leads to this initiative that we are thinking of starting. The idea is to establish this common research configuration that we could use to sort of focus as a reference model, as a reference configuration to converge and connect different enabling technologies. So this is what we have been working on with the University of Maryland. So this is a quad biplane that would be our platform as a benchmark platform, and with focus on making advances along these 3 basic areas, or 3 component areas. Now, so the idea of reference vehicle is fairly common. NASA used common reference model, then which went on is still active, has led to big contributions to state of art. US-60 is a good example for our community, which was subject of annual workshops for 17 years. So our goal is to pick some of those ideas from these similar programs and sort of build or expand our common research configuration program to make further advances. Now, finally, I guess one question that I get asked, or you may ask, is why quad biplane? And here is a response to that. So basically, we do need a benchmark concept. It's a quad biplane is a nice US concept that has essential elements of VTOL US, simpler design, which is really nice to have for research needs. And there's also a good amount of history, especially at Maryland and for the last 3-4 years with us. So we have looked at a couple of scales, and our goal is to keep up going on the scale and develop the knowledge. And with that, I'll conclude. And again, just want to end with another opinion, another fact. And my opinion is that eVTOL is disruptive technologies for Army. And the fact is that ARL is looking forward for collaboration with any one of you here. If you are working on Army challenges, then we can go out of way to work with you. That's all.
Thank you, Rajneesh. Our last speaker on the panel, Professor Chopra, needs a little introduction in this room, I believe. He's had an illustrious career, graduated from MIT in 1977, spent several years out at NASA and Stanford University, where he then joined the University of Maryland in 1981. And the legacy that he's really created coming out of the University of Maryland, I think, is second to none. and unparalleled across the community. And he's been recognized with numerous achievements and awards across his career, including probably some of his most prominent things, which he would love to, I'm sure, talk about, is the 54 PhD students and 100+ grad students that have come out of that group and are really making a tremendous impact across the rotorcraft industry today. And so, from the numerous awards that I'm sure many of you have heard about, 2002, the AIAA-STM Award, the AHS Grover Bell Award, ASME Adaptive Structures and Materials Systems Prize, the Clark School Engineering Faculty Outstanding Research Award, the SPIE Smart Structures and Materials Lifetime Achievement Award, the Indian Institute of Science and Centenary Distinguished Alumni Award, several awards from AHS, including the Alexander Clement Award, the Igor Sikorsky International Trophy, the Nikolsky Honorary Lecture Award, AIAA Fellow Award, as well as the ASME Spirit of St. Louis Award. He's a technical fellow both of AIAA and an honorary fellow of AHS and a fellow of ASME. But without further ado, we can go on for hours talking about the tremendous accomplishments you have, but we're really honored to have you up here and serving on the panel. And without further ado, please come up, and we'd love to hear what you have to say about eVTOL.
For me, it's a matter of pride, when you see your student go outside and do very well. And Farhan, you're doing a fantastic job here. I'm really proud of you. Congratulations to RPI. I think they're doing a very good job. I'm going to talk about, this was part of my Nikolsky lecture, but it's a short version, so not like there it was much bigger. So let's start to the definition. What I mean is small UAS or delivery drones. I think Rajneesh mentioned that the DoD has divided these unmanned into 5 categories. I'm going to talk about the last category, Group 1, which is of course less than 20 pounds or 10 kilograms. That's the yellow one on the top. These are some of the aircrafts. Also under this category, also can mention like micro air vehicle people call. These are about 100 grams or less. Nano air vehicles, which is less than 25 grams. Or pico air vehicle, which is less than 10 grams. These are tiny, more like sensors. Then I think in the last, of course, 3 years, this new thing came up with the delivery drone. And to just get a feel, if you take a payload of 5 pounds, which is more than 2 kilograms, it covers 86% of the Amazon delivery packages. So within a radius of about 10 miles. So Google and Amazon working separately to develop these vehicles, like Google is looking at tail sitter, which is 4 rotors. And Amazon started with octocopter. And then of course they moved to have many other derivatives. Beside these 2 companies, there are many other companies working in these. It's looking at, for example, Domino's looking for pizza delivery. I think it's fascinating to see so many companies working in this area. What are the major challenges? Of course, the size. It's a small, weight, and power, what we call swap. And that's a big constraint. Lower number aerodynamics, which means the performance is going to be limited. And gust, big issue, especially near the ground, because the disturbance is the same order as the capability of the vehicle. So this is what I'm going to talk about, small scale sustained power generation. And of course, these guys are going to operate in an obstacle-rich environment. How big it is, market. Just these are small vehicles. So as you can see, exponential. This is in millions. The next one gives you a little better feel. The gray one at the bottom is the DoD. The market is more or less saturated. The top one is a hobbyist. Also again saturated. It's not going to change much. The middle one, the pink one, which is the commercial, is growing rapidly. And the next one gives you a feel, like 2020 is going to be $25 billion market. This is without excluding the delivery drone. If the delivery drones are covered, it will be triple. So this is probably amazing. I think 3 years ago, EHS had this student design competition to have a delivery drone. And so we just covered in the area of Washington, D.C. and suburb, taking a radius of 50 miles by 15 miles. And today, I mean, it's almost like 5,000 packages are delivered. In a peak time, it will be almost like over 400 packages, 443, which means there will be 300 vehicles being used in a day. So at the same time, one time. So here is the picture, what's going to be like the central, basically warehouse, of course the customer, the delivery drone, and of course the communication with them. And you can see how these things go. See? This is going to be the market, all autonomous. From the warehouse right in the middle, how these vehicle will be being done. So you call the company and everything autonomous. So I think DARPA gave this challenge of 100 grams, 60 minutes. Not many vehicles have reached there after almost like 15 years, because there are a lot of challenges. So fixed wing can do it, but not the rotary wing. So taking a rotary wing, these are all, you see the construction, you need a rotor, you need a payload, of course, airframe, navigation, sensors, and the red one, which I'm going to talk. Let's talk about propulsion, because this is more like to be electric motors, battery there, and also maybe. So coming back to, you need a DC motors for small vehicles. The brushed motor, okay. As you can see, these are of course very simple. The magnets are stationary, the coils are rotating, and of course, these, because of brush friction, they don't last long. Very good for when you have a very small weight, say less than 100 grams. More than 100 grams, then you'd go to brushless motor, which are more popular. No friction, okay? But the biggest thing is these electron control is very complicated. So it's heavier, good for more than 100 grams. The problem with also brush motor is that the maximum efficiency for a very small, what you have is a power versus efficiency. So it's in a very narrow range. Whereas the brushless is much better that way. But they are heavy and they are more complex, because you need to provide a phased voltage. So other problem is, as you start reducing the weight, the efficiency falls rapidly. For some of these small motors, you can get even single digit efficiency is a big deal. However, when you go to very large motors, okay, you can get very efficient all the way to 95%. So you have to be very, very careful. So a whole lot of questions people ask. The motors, they're not much knowledge base at the bottom side because there was not much market. Now people start looking at it. So coming back to the motor conclusion, of course, brushless motor and is probably the way to go for more than 100 grams. And of course, efficiency decreases with lower size. Okay. And of course, that's the way to go. Recommendation is examine, of course, electromagnetic for these small size which have not been explored very well. And come back with a better, this efficient speed controller for brushless motor. Coming back to the battery, a lot of things people talk about with batteries. And man, there's enormous things are going on. This is probably the most hot topic right now in academic circle. You go any institution, you can find 8, 10, 15 people working in motors. Of course, you look at lithium oil battery is the famous one, but this is what I want to show. You have two axes. On the left side is energy density. the total energy stored in the battery divided by the volume. The right-hand side is specific energy, which is the total energy stored in the battery divided by the weight. In the last 15 years, it's like a Moore's law. There have been 8% yearly increase in the battery capacity. So it's not batteries are not sitting idle. So people who think nothing is happening, and you haven't seen nothing has come out, because when I look at academic, they're telling even twice of this, so 3 times. So things are going to change. What's happening in the batteries? Specific energy is going up. Price is going down. And the life of the battery is going up. Recharge time is going down. That's because of electric people. All these other factors are because of cell technology. And the flexibility, also the batteries are becoming more flexible. Okay. Let's talk about IC engines now, internal combustion engine. When you look at like a specific energy of hydrocarbon fuel, it's about 100 times of electrochemical material used in battery. So very little fuel has so much energy in it. So why we're not using it? The problem is right here at the bottom. When you started reducing the weight, okay, the efficiency fall very rapidly. Okay. And of course, because of increased losses with heat transfer, because when you have a small thing, where do you send the heat? Fluid friction, leakage, and all those things, efficiency rapidly fall. We need to come up, this is where the nanotechnology has to come. Material with a higher thermal isolation, okay, increased combustion efficiency, and of course somehow to control the acoustic. Acoustics are terrible. These are small motors, small, enormous noise. So once we overcome these things, hey, there's a tons of energy. All you need is basically have a proper alternative with that. So coming back to small unmanned aircraft, which we're talking about, okay, there is, if you are thinking non-hovering, fixed wing. Rotary wing, there are a whole lot of things, single, coaxial, shrouded, quad, unconventional rotor system. And if you want to get a high speed, forward speed, long range, then you need to go to compound. Tilt rotor, tilt wing, tail sitter. Okay. Also possible flapping. Of course, these are too complex to build right now. If you go to insect base, okay, you can hover. If you go to avian base, you can go long distance, you can go high speed, but you cannot hover. Reaction base is not probably a good idea because very power intensive. So coming back to compound, I think Rajneesh was talking about it. You need both hover efficiency as well as cruise efficiency. Then you go to the compound, tail sitter, tilt rotor, tilt wing, all these things are possible. The biggest challenge in these things is transition flight. Helicopter to fixed wing and the reverse. And even if you're looking at the blade twist, then you have to have a proper compromise. RPM is absolutely needed to change the RPM from both modes. So here is, of course, quad biplane. Here, helicopter mode, airplane mode. This is about a 5-pound vacuum. So coming back to key challenges, of course, you need efficient aeromechanics, which will be a high figure of merit, of power loading, and also high cruise L over D. Electric motor with high operating efficiency over a wide operating conditions. Variable RPM capability. So also think in terms of, there are a lot of issues related to coupling these motors with the rotor, need a stability in both. And minimize, eliminate rectifier or inverter because that's additional weight and low acoustic signature. Here's one of the examples. I thought some people will talk, but I haven't talked. You don't need to use the battery all the time. If you can have a, like in this case, that for most of the cruise condition can be done by, as you can see, is by the fuel stack. Okay. The problem is also fuel stack technology also moving very rapidly because of the electric company, by automobiles. And there may be a possibility you may not, you need a battery. Battery you may need only as an augment in a hover condition, takeoff and landing. Batteries are of course too heavy for long range at this time. Hydrogen fuel cell can be a promising alternative. Hybrid internal combustion electric can be also near-term solution. So, and of course the future is, people haven't paid as much attention to the motor side, high torque, low RPM motor, that's the future. If we can come up with a good motor with the high torque, it means we don't need a transmission, enormous reduction of weight. Design, and most of these vehicles which have been built, they are all built basically ad hoc. If you start building a vehicle for a specific mission, then you can optimize it. And there are a lot more need to be done. Okay. So where were we, say, 10 years ago? Mostly it was fixed wing at that time. Today, of course, all quad rotor. The future is going to be more hybrid. 15 years or 10 years ago, people didn't think of payload, but now it is a modest payload. But I think, again, I said the future is more mission-based. Propulsion, all battery, but the next is going to be all combination, battery, fuel cell, and so on and so forth. So as we say, it is a multidisciplinary system where you need to have aeromechanics, micropropulsion, microelectronics, microprocessing, fabrication, navigation, everything together. The real, of course, challenge is efficient and sustained power. I'll probably conclude it here. Thank you.
Thank you, Dr. Chopra. I know we're running a little bit late, but if we could have the panel members come up, maybe for like 10 or 15 minutes or so, we can just have a quick question and answer session for any burning questions that folks might have related to some of the talks that they just saw.
I have a question relating to the motor concept. You know, when the gas turbine engine was introduced, let's remember that the power-to-weight ratio of the IC engine was 1-to-1. Really, that's what it was. And then when we started introducing gas turbines and approached 4 and 5-to-1, people were absolutely amazed. Matter of fact, there were people who thought it was reverse, frankly, that we had it upside down. That's what made the modern helicopter, really. That's what made the Black Hawk. That's what made the Apache. In the 1950s, we didn't have it. So that was an enormous revolution in power-to-weight ratio. Even though the thermodynamics of the Brayton cycle wasn't as good as, let's say, the Otto cycle was, we only flew like 4 hours, so it really didn't matter as much. Now, in order to move into this new revolution, we've got to produce these motors systems, which means the motor, the generator, the motor, the converter, the inverter, the cabling, the thermal management systems at competitive weight situations. And the concern that some designers have is that you can't do it. So they back into the conventional, this is for, say, distributed propulsion system. They back into the conventional gearbox situation. So I have a question with that background, first of Aurora. You had a concept, lightning strike, right? Lightning strike, which received DARPA funding, and it was an AC motor, which was very interesting. You had AC generators and AC motors that never needed the conversions, or the converter or inverter, but it meant you had to phase all of the electric machinery properly. At the time, there was some confusion about that over a, well, let me use the word, a more conventional DC system that Dr. Chopra was showing. Now, I just wondered if you might comment on that. In other words, I am sort of prejudiced towards the DC systems, but that could be all wrong. So I just wonder what your thoughts are along those lines.
Yeah, I mean, thank you for the question. I personally am not that tied into the lightning strike, and so I would not be able to give you an answer, but I'd be happy to connect you with the right people for that. So I apologize for not.
Does anybody else on the panel want to comment on that?
So, from what I know from discussions with some of the DARPA, from Aurora guys, that initially they did look at DC as the primary means, but ultimately I think it looks like the weight for AC system turned out to be lower than if they had gone with the DC system.
That's correct. But there were other electrical machinery problems that became extremely difficult. I understand this, but I really haven't had it confirmed. I just want to understand whether or not that's true, or is it folklore?
From what I know, it is true. Well, again, I cannot speak for should not speak for Aurora.
Okay, I'll leave it at that. Thank you.
So thank you very much. It was very enlightening. I'm sort of from outside somewhat of the rotorcraft community, even though I've been working in it for the past few years. My interest is in autonomy. And so one of the things I was curious if you were thinking about some sort of plug and play replacement of components, because one of the issues are you have lots of subsystems, right? Several subsystems. And certification is not just of the entire craft, but it's easier to certify bits and pieces, and somehow you combine that certification into one big certificate for the entire operation. So is that the approach that autonomy is taking, or is it the opposite, where you try to go top down and say, here's the overall craft is certified, individual pieces, not so much important?
So I think the way we're thinking about it is there's both vehicle-specific systems, and then there's also, as we described it, kind of a core system that would be agnostic to the vehicle. And so we're really focused on certifying that core system that then could be applied to each of the vehicles, but then there's going to be pieces that tie into it that are specific to each vehicle that it goes on to. So I think that it's both.
And so you can swap parts in and out. Let's say you switch your AI algorithm.
Yeah, they're not in the core system, but then in the periphery systems that plug into it.
I had a question on like the life cycle. So I think there's a lot of talk about how many of these unmanned vehicles are going to be in the air, and we don't have enough pilots for them. But on the life cycle, the maintenance, I mean, are you going to have A&P mechanics, huge, quantities, and how are you going to tie your weight fraction to onboard health and usage monitoring and, spare parts and inspections of these aircraft that are going to be, over people's heads to ensure that, they're maintained and flying properly as a fleet and coordinated, and, the ground support, I guess, is going to be a big, large.
I think the key there is to get into a remove and replace scenario. I think if you start to bring qualified A&P mechanics up onto the aircraft to do, traditional maintenance of a system that's on board, you start to run your direct operating cost up through the roof. So you need to, we're thinking about it more as LRPs, remove those units, get them back to the place where they're most efficiently maintained, repaired, and overhauled, which is the factory, and have a simple scenario to replace those just on site. So, of course, that's not not the case with the hybrid. You still have your gas turbine on board, but as you move more and more towards all electric systems, I think you need to think about it as an LRP.
I have a question regarding the pilots and the current vertical flight industry. Most of my colleagues in conventional vertical flight in the commercial world, up in Canada and elsewhere, this is not even in their peripheral vision yet. And I guess there's a cultural shift coming, or there's some kind of shift coming where who are the early adopters going to be, the people that are going to be going into that pilot stream versus being, say, wooed by the airlines or out of the helicopter cockpits. How is this going to play out in terms of being able to prep the ground for the manpower requirements?
We think about that a bit. It's a good observation when you take a slice of the Bell pilots. We find a couple that want to come down and do a lot of work with us on simplified vehicle operation. we kind of think about it as, we call them future aviators, and we think they trend more along current technology trends than they do, traditional controls to a future, change in that same setup. You look at kids today, they always have an intuitive interface. They're used to having, symbols, cryptology, interface with them and make decisions based on that. I think we have to think about a cockpit that addresses more of what we see in today's everyday technology that's out there, from cell phones to computers to game controllers, that can help us with the future state of aircraft control, or VTOL control in particular.
Who's doing that?
Well, we're studying it. We're trying to come up with a couple different cockpits right now for our eVTOL vehicle, maybe give a look to the public to see how it feels from a today pilot and a person that's not a pilot, maybe a pilot tomorrow though. So we're gonna use kind of simple X-wing simulator kind of model and put some controls around it to see how people react to it and see if they can complete some missions. We're looking at a few things like that from the OEM side.
Yeah, I had another question, and really Scott's probably the best guy to answer it. All of us introduced HUMS and prognostics, diagnostics. Now it's more than almost 3 decades. But it occurs to me that the level of diagnostics and prognostics that we're going to have to talk about when I'm coming out of my garage with this aircraft, and I'm going to fly it. I'm my own A&E mechanic, let's say. Okay, but I really am not an A&E mechanic. I'm Ken, who just wants to get into the aircraft. This aircraft has got to be at a state of self-test and self-awareness, and with an implicitly not only safe, but we've got to have a huge knowledge of its state or its coming state that's entirely different than what we are today. So I just wondered if you're doing anything about it, and it certainly would be a challenge for this center to be thinking a little bit more about, I saw some stuff talking to a student the other day, but it seems to me that it's got to be a step above that if we're going to get to this new world. In other words, I'm going to use Sikorsky's Matrix as an example. It's geared, I think, like yours is, to flight management, to aviate, navigate, all those sort of things, with perhaps a worldview applique. But the issue of the prognostics and diagnostics and that enormous challenge we have here, I think has to have its own centroid. We have to really begin to create challenges that transcend where we've been to date. And I just wonder, Scott, if you're thinking about it for you. You seem to have done a lot of thinking about the business aspects of it, and that's why I'm addressing this question to you.
Sure, thanks, Ken. I think it's a great idea for a place like RPI and the Move Center to think more about the IVHM systems. We're working on it right now, primarily on the 525. It's a big project with the 525 and some of our other legacy vehicles. I agree with you. It's going to have to, make its way from the initiation of the design and call it a digital twin or whatever you like. You have to know about the state of that component from the day it's created all the way through its mission and out to the service, the moment of service. I think we need to take into consideration too that we oftentimes design things to a peak load condition. We need to start taking credit for the real mission that's occurring on the vehicle itself. We're not going to be slinging logs with these aircraft. We're going to be hopefully fixing the mission within some reasonable parameters, and we have to take advantage of that as well. So it's a real-time state of knowledge.
For example, the ground-air-ground part of the operating spectrum is significant. Let's go with the Goober model.
I'll tell Mark you said that.
But the Uber, the question is, he's going to have an awful lot of ground-air-ground cycles, and in our fatigue light calculation, that can become extremely important from a weight point of view, very important from a weight point of view. So you're going to get to a point where some of our components are going to reach life limits. Now, we can't do that by a log anymore. This guy's going to get in the airplane, push the button.
Yep.
Now, if he's got components that are exceeding that limit, I'm sorry, you can't fly. Big thing comes up, you can't fly. Now, we give him notice early in the game, way before that event, but we have to actually preclude him from flying.
Absolutely.
So that's a whole new concept of management of these vehicles. It could result in litigation issues.
I'll just say, you also mentioned, pulling out of your garage, and now we get down to the individual commercial transport as opposed to kind of the industrial transport where we kind of manage it more universally. And I think from Chris's perspective, kind of pulling a vehicle that I want to give to an individual, they're not going to have the skill set to understand how to fix these things and whether or not they're at a state that they need sensing. So from, let's say, Terrafugia's perspective, are you guys looking at anything to kind of think about how you would bring that capability down to the individual side of the house so they can understand the state of that platform so that they fly it when it's safe and when
I think, honestly, when we're talking about the Uber kind of operations, these are vehicles that are much more expensive, much more complicated than an individual owner is going to be willing to operate, right? So this is really fleet kinds of operations and a very different situation, right? Our first product is one that you can keep in your garage and you can maintain yourself, right? But I think what we're really talking about with the eVTOL process is much more complicated than that, right? You build in all the automated diagnostics you can that's possible, but you're not going to have mom and pop maintaining your aircraft. It's not going to be Ken's garage, right? It's going to be the Uber fleet, right? It's that kind of a situation. And then you are going to have A&Ps. While you want to move fast on the pad or at your vertiport, you want to be able to swap out the equipment, the aircraft's still going to have to go back to the barn at night for regular kinds of maintenance, right? I want to make one more comment about the pilot issue, though. There have been demonstrated cases, and I think they're not well advertised, publicized. Garmin ran a test with a Bonanza, and they put in a simplified operating system. And they spent 15 minutes with the administrative assistant training them, and that lady went off and flew from taxi to touchdown with no further instruction. Right? It was done a couple of years ago, right? This stuff exists. The F-35 is another fabulous example, right? Look at the accident rate that the Harrier had. How many years did it take to debug that in Britain and here with McDonnell, right? The 35 has had nothing like that kind of troubles because they focused on simplifying pilot operations, right? How many fatalities in the F-35 in the vertical takeoff version development program? None. Right? So that stuff's in place today. We need to go tap into that in our business, right? We need to bring that into the fold with us. And it's another excellent area for investigations here.
I guess we have time for one more question.
That sparked up. All right, so another pilot. Oh, what were you saying? Yeah, another question, the pilot thing. So if you look at Kitty Hawk, which is a company in Silicon Valley who's building like a small flyer drone that you fly over a lake. And then if you look at like eVTOL, they're I'm gonna have the last word now. Awesome. Basically, just if you look at the business model for some of these small startups that are actually letting you fly these aircraft soon, they just have 1 day of training, and they're basically in the air flying these things around. And I think all you have to learn how to do eventually is do the contingencies and go up, over, down. And I think that the autonomy will be part of those simplified operations, and therefore you won't have to have major training.